Hi everyone, today we're looking at natural logarithms. And natural logarithm means that we have a log base e. E is an irrational number approximately equal to 2.71828. Exponential functions with a base of e are useful for describing continuous growth or decay. So we're going to be using the formula for continuous compounded interest, which we often refer to as PERT. The final amount A is equal to the principal E raised to the RT power, where R is the interest rate and T is the time. On your graphing calculator, if you do second division symbol, you'll get the E, or if you want to have E raised to a power, you could use the second ln button. So the graphing calculator has a key for E and a key for E raised to a power. So we're going to look at some continuous compounded interest problems. Suppose you invest $10.50 at an annual interest rate of 5.5% compounded continuously. Now this is what you're looking for, these key words. When we see compounded continuously, we know that we're going to be using the PERT formula. How much money to the nearest dollar will you have in the account after 5 years? So let's write out the formula. A equals P E to the RT. Now, it says we invested $1,050. So that was our initial investment. We have E, and just want to underline compounded continuously so we know we're using PERT. The interest rate is 5.5%, which we need to convert to a decimal, so that's 0.055. And over 5 years, so the value of T is 5. All right, let's put that in the calculator. We're going to use second ln. We have 0.055 times 5. All right, and we get a value in the account after 5 years, rounded to the nearest dollar, of 1,382. All right, let's try another one. Tommy opened a savings account 1 year ago. The account earns 4% interest compounded continuously. There's our keyword to know that we're using our PERT formula. If the current balance is $700, how much did he deposit initially, rounded to the nearest dollar? All right, so this time we're looking to find the initial amount. We already know that once we've compounded the interest continuously, we're getting an output value of $700. So this time A is 700. We don't know our principal, our initial amount. We have E. We have our interest. When we write that as a decimal, we get 0.04. And this is happening over a 1-year period, so T is equal to 1. All right, so in order to solve this, we have to divide both sides by E raised to the 0.04 power. And that'll give us our principal. Let's put that in the calculator. And rounded to the nearest dollar, we get $673. So natural logarithms, again, are when we have a base of e. And we've looked at this a little bit in the previous lesson, and we're noting it again here. Log base e can just be rewritten as ln. A natural logarithm is a logarithm that uses base e. If you see ln and you feel confused, just rewrite it as log base e. The properties of common logs that we've already looked at also are going to apply to natural logs. So this is really a good repetition now of you getting used to the properties of logs. So Here we're being asked to condense each expression. So in other words, we want to write this as a single log. In this case, these are all log base e, which we're writing as ln. So we're going to use the power rule to bring this guy up. And whenever we have subtraction between, that becomes division when we condense the log. And 2 to the 5th divided by 4 is 8. So our final answer here, once we've condensed it, is ln of 8. And you always just want to have the word log in your final expression, in this case, ln. Okay, we're going to leapfrog that 3 up, the power property. And because we have addition between, we're going to have multiplication. So we're going to end up with ln x cubed y. All right, again, we're going to have that power property where we're bringing up the 1/4 for both of these. So we have ln 3 to the 1/4 power plus ln of x to the 1/4 power. We have addition, so when we condense the log, it's going to be multiplication. Right, and that certainly counts as condensing, but since they're both raised to the 1/4 power, I'm just going to rewrite that. I think this just looks a little bit nicer. But either of these would be an acceptable answer. You can turn in this guy or this guy. They would both work. Now it says use the properties of logs to solve logarithmic equations. All right, so we have ln of x equals 0.01. So we want to take this and rewrite it as an exponential equation. That's going to help us solve it. Now, if you don't, feel comfortable seeing that ln, you may want to just rewrite it as log base e of x equals 0.1. Now you just remember that to convert it back to an exponent, e to the 0.1 equals x. E to the 0.1 equals x. We're going to round this to the nearest hundredths. So we're going to go back to our calculator. And that gives us approximately 1.11. All right, let's try the next one. I'm going to rewrite it. Log base e of 3x minus 9 equals 21. I'm going to put this in exponential form. E to the 21st power equals 3x minus 9. In order to solve this, we're going to add 9 to both sides to start. And then we're going to divide both sides by 3. So x is going to be e to the 21st power plus 9 divided by 3. Okay, last one you should try on your own and then come back when you're ready. E to the 12th equals x plus 2 over 3. We'll cross multiply. So we're going to get 3e to the 12th equals x plus 2. So x is equal to 3e to the 12th minus 2. And rounded to the nearest hundredth, we get 488,262.37. We can also use natural logarithms to solve exponential equations. And I just have a reminder in this little box here that ln of e equals 1. If you recall that I told you that if you have log base e of e, that would equal 1. Just like if you have log base 10 of 10, that equals 1. or log base 3 of 3, that equals 1. So ln of e, which is just log base e of e, is equal to 1. It's helpful to remember that when we do these kinds of problems. So we're going to take the ln of both sides. We're going to take log base e of both sides. And why do we do that? Because ln of e is 1. Log base e of e is 1. So this piece right here becomes 1, and the exponent is just going to power property back to the front. So the left side of this equation is just going to end up being x plus 1. It becomes a very simple equation very quickly. So x is going to be equal to ln of 30 minus 1. We'll use the ln button on the calculator. It's highlighted in red. Make sure you close parentheses. And rounded to the nearest hundredth, we get 2.40. All right, now before we start letter B, we want to isolate E. We need this part of the equation by itself, or it's just going to get way too complicated. So what we're going to do is we're going to subtract 7.2 from both sides. All right, so that's going to leave E by itself on the left side. And then 9.1 minus 7.2 is 1.9. All right, now we can take the ln of both sides. The ln of e is just going to be, this part is just equal to 1, and this is going to leapfrog to the front. So on the left side of the equation, we have 2x over 5, and on the right side, we still have ln of 1.9. And we'll cross multiply. All right, so we're going to end up with, I'm going to continue over here. Let's say 5 ln 1.9 equals 2x. Divide both sides by 2. And we're going to end up with x equals 5 ln 1.9 divided by 2. And that gives us approximately 1.60. You can use natural logs when dealing with equations involving continuously compounded interest, we're back to PERT, to solve for the interest or for the number of years. So in other words, if you have a variable as an exponent in your equation and you need to solve, the natural logs are going to come in handy here. So I'll show you what I mean. We have an investment of $100. It's now valued at 149.18. The interest rate was 8% compounded continuously. How long has the money been invested round to the nearest year? So if we write out our PERT formula, this time we're looking for how long has the money been invested. So T is going to be what we're solving for. So let's fill in everything else. The final amount is 149.18. The initial amount is 100. Our rate is 8%, but if we convert that to a decimal, that's 0.08. T is what we're trying to solve. All right, so just like in the previous problems, we isolated E first. The first thing that we want to do here is divide both sides by 100. So then on the left side of the equation, we end up with 1.4918, and over here, e to the 0.08t. Okay, that looks a lot better. Now, we want to be able to use a log to help us bring that 0.08t out front, bring it down from being a variable. So we're going to take the ln of both sides. All right, the ln of e is just 1, and this part is going to leapfrog to the front because we can use our wonderful power property to bring that out front. So the right side of the equation just becomes 0.08t. And then to solve for t, we're just going to divide both sides by 0.08. All right, let's put that in the calculator. And we're looking to round how many years to the nearest year. And so in this case, we have approximately 5 years. All right, I would try number 7 on your own, and when you're ready, come back to the video. An initial investment of $200 is worth $315.24 after 7 years of continuously compounding, right? So we know we're using per. Find the interest rate, round values to the nearest thousandth. So we're looking for a rate, we're rounding to the nearest thousandth. So if you're not sure where to start, the best thing to do is just write the formula out and see what you can fill in. So we know that the account is now worth $315.24. Our initial value was $200. We are trying to find the rate, so we know R is going to be there. And we know that our time is given as 7 years. So we have E raised to the 7R. We're going to isolate E, divide both sides by 200. So the left side of the equation is 1.5762. We're going to need a log so that we can bring that 7R back down. So we're going to take the ln of both sides. ln of E is 1. So 7R can leapfrog to the front. Divide both sides by 7 to solve for R. I'm going to take the ln of our answer, save a little typing there, and then we're going to divide that by 7. Rounded to the nearest thousandth, we get 0.065 for our rate. And if we want to write that as a percent, 6.5%. All right, that's it for this lesson. Thanks for watching. Have a great day.